We show you an example. The voltage of this, let's check the voltage of this plug. 125 volts.
Wasn't just 123?
125, what we got right now? 125 volts, all right? So let's check and see what your resistance is. So we're going to turn it to ohms. Hold one side, hold the other side. The resistance of your body is 1.9 ohms of resistance. 1.9. So 1.9. So if you were to touch that wire and slip and touch anything, maybe the ground, actually dirt, or the other side of the plug, or anything else, the resistance of your body is 1.9 ohms of resistance. The plug here has 125 volts of electrical force, of potential difference. So what's 125 divided by 1.9? That means there would be going across your heart, because from here to here is what? 65 amps. It takes less than half an amp to kill you. There'd be going from one of your hands to the other 65 amps. You would not survive that.
So people that get hit with lightning are just really lucky if they survive?
Well, there's a lot of force there, and it does depend on how the flow of electricity is. A lot of lightning is going to ground. It's going everywhere around them as well, and it depends on how it's flowing. But yeah, if you get struck by lightning, then basically you're lucky to be alive. Yep.
Well, scientifically, how are you alive? Just luck?
I've never been struck by lightning, so it's. I see a storm, I don't take the chance. I walk inside.
Well, am I right? Does everybody have their own resistance? Like, is everybody gonna be at 1.3? 1.9?
I don't know. It's a good question. Let's find out. Let's find out.
Let's answer that question.
I can't see it now.
Hold on.
Hey. Don't stab me twice.
Don't be grabbing my probes,
you stabbed
yo.
first, man, and then you took it back like let me.
You
stab
just don't
you
reach for
again.
another man's probes, you know?
I don't want to hold them now.
All right, so your resistance is 325.
What? Told you to get your numbers at one. Damn, son.
How's that possible?
Pretty good chance you'd survive that same scenario.
Damn, dude, because the hair and the mustache.
How's that possible?
That's what I'm talking
What are you
about.
made of?
Yeah.
Rubber?
Your resistance is 206.
What the? You scared me, man. All the times I got listen to you, stop.
Yeah, dude, just put all your resistance away, man. You can't get hit no more times. Dang.
136.
See,
How are you alive?
Yeah.
If someone put on a light switch, you get electrocuted.
1.5.
Oh, okay. Hey, welcome.
I thought it was just because you're a black baby. I didn't know. Oh, 0.4.
Whoa! I mean, how much you touch it every day? Man, now yours is gone.
Get pushed around. Dr. Pepper, man.
Yes.
80.
Oh, there's if that guy over there holding your mind,
285. 114.
Hey, let him do you again, man.
0.5.
Don't touch it like this.
Lower your resistance,
Move
the
your
less
hands apart.
stressed you are? Is that what it is?
Not necessarily. Keep your hands apart.
Not necessarily, so that could be one.
This is a huge...
0.3. 69.
Yeah!
0.4.
that's outstanding.
0.6.
Some of these people are less than one.
1. 201. 196. 201.
There you go.
0.5.
0.5. Too mellow, man.
88.
I've been shocked too much.
She looks, she got 500.
0.5.
Oh, snap.
I've been shocked one too many times. I'm like,
1.3. Every person or you say every body has a different amount of resistance. Every body has a different amount of resistance, right? The body actually works off of electricity. How your central nervous system, everything's working, communications, it's all working off of electricity. And there's a lot of things that affect how your body operates. For one is how well hydrated are you? How many electrolytes have you had? Have you been drinking as somebody that drinks just water may not do as well as somebody that drinks water with electrolytes, right? Helps that also balance out. Other things like fats and hydration and how well are you rested? How well is your body's electrical system working? There's 100,000 variables that go into this about how this works. And whatever you have today could be different in an hour from now or tomorrow or in the morning, whatever. It could all be different and change. So it's not a set number. But if you have really high resistance, maybe you should go get a bottle of water or something. Jeez.
I was gonna say, I'm like, I ain't drank water in like 6 years, so I'm like,
well, there we go. There we go.
I'm gonna keep doing what I'm doing then. 325 ain't bad. I'll survive a shock. I won't survive life. I'll probably be dead by 60, but 325, baby, I won't die from the hands.
But that's just if you touched here and here. There's other scenarios. If you touched here and there or touched here to here. I did that scenario because as electricity would flow across your heart, then it brings that down to what. But just to get you thinking about amps, volts, and ohms and how they all tie in together. Pretty cool, huh? So with amps, what we do is when we're checking amps, we clamp the meter around a wire. Clamp the meter around the wire. With ohms, with resistance, we use the leads. Right, we use the leads, but we also want to make sure it's off and isolated. Sound good? So far, so good? Electricity, right there. So they make this cool little toy, very similar for us. And what it has over here is this hole. And with this hole, what I can do, it's called a line splitter. It takes these two wires and it separates them. So if I clamp my meter around this wire right here and have it running, it tells me the amps. It also has two little holes in it. I can also put my volts meter and hook it here and here, and I can check the volts while it's operating. It's a pretty neat little toy, right?
What you gotta set that for?
Right now it's set on off. I just turned it to volts. And this is a dual display, which is cool. The top number says A, so what do you think that's reading? Amps. Right, and the bottom number says V, so you think that's reading? Volts. Right. Pretty neat, huh? Pass it around. You guys can see it. I'm not ready to show you this yet. What we're going to talk about. All right, so questions yet so far? All right. Well, let's continue on down this journey.
So if we have an electrical current in our body and we touch both of those welds on that, should it get a reading?
On volts? But there's probably not a potential difference, though.
Okay.
You have to find wherever your electrical energy is starting from and find another point.
You can't just touch one because it's the same as we're all one thing, so it doesn't work that way.
Right, exactly. Good question.
We're gonna cover all the symbols, right?
Not all of them. It would take me a lifetime to cover all of them. There's lots and lots of symbols. We're going to cover the main ones.
And they're adding new ones as we're having this conversation.
They absolutely are. Without a doubt they are. And every manufacturer gets to pick what symbol they want to use. That's right. I prefer the drums over the symbol. As electricity flows through a wire, it creates a magnetic field around that wire. Pretty neat, huh? If there's no flow of electrons, there's no magnetic field. The faster the electrons are flowing through that wire, the stronger that magnetic field becomes. Do you know that? That? You should say that again. As electrons flow through a wire, it creates an electromagnetic field. The faster electrons flow, the more powerful that magnetic field becomes. So in our clamp meter, as we clamp the meter around that wire, this is reading the electromagnetic field of that wire. The stronger the magnetic field, the more the amps. The weaker that magnetic field, the less the amps are. So when we clamp it around that wire, and it's giving us a reading, it's doing it by checking the electromagnetic field of the wire. Because electricity and magnetism go hand in hand. Have anybody done any welding in here? Stick welding, arc welding? Okay, cool. You guys ever done it in a metal shop? Okay, what else do you have in the metal shop? Clamps? What else is going on? You cut any metal there? Yeah, grinders, right? Chop saws. So what ended up on the floor?
Shavings.
Metal shavings, that's right, metal shavings. Have you ever noticed when you're welding with that big wire going on the floor that sometimes you'll see those metal shavings next to the wire will be lined up? However that wire is laid, those metal shavings will be lined up. That's because the electromagnetic field of that wire. Those welders, high amount of amperage, as those electrons are flowing through that wire at a fast pace, creates a very strong magnetic field, and all those metal shavings, fling, pull sideways, and they line up with that electromagnetic field. How cool is that? Pretty neat, huh?
Well, that's why, like, you can take a screwdriver and wrap the wire around it, it makes it magnetic.
So what we have here is a magnet with some metal shavings. So you guys can kind of see the magnetic field of a magnet. And if you open it up, you can see.
It's a woolly willy.
Some people have pet rocks. This is my pet shavings. Right? It's like Frodo, it's just Fro. So I'll pass this around. You guys can get an idea of what a magnetic field is. Cool, huh? Magnetic field. Look at it. It's so cool.
Did you create that?
Electricity, though, it's not making two different ones. Like this is, you can see the positive side, the negative side, and how they're connecting and all that. But it's just straight lines and circle like rings around it. I did not make that. I wish they did. So what happens to this electromagnetic field if I take this wire and I go around itself? What happens to my magnetic field here?
Becomes stronger in that area.
Yes! It becomes stronger in this area. How much stronger do you think it becomes?
Twice as strong.
Twice as strong. I've taken that magnetic field, I've wrapped it around on itself, and I've increased the magnetic field double. Pretty cool, huh? What if I go around 10 times? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
10 times.
It's 10 times as strong. How awesome is that? It is cool. It's 10 times cooler.
Is that how I make magnets?
It is. We'll get there. So here I got this line splitter, and let's say I have a phone charger. Phone chargers use a very small amount of amperage, right? Very small. It's very difficult to read it with that clamp-on meter because the electromagnetic field is so weak. It's weak, right? So what we can do is wrap a wire around 10 times, then clamp our meter on it, and it's going to be 10 times more powerful. So whatever number I get, let's say it said my number was 4.5 amps, I'm going to move that decimal over one spot. It'd mean it'd be pulling 0.45 amps. So what's cool about this is it has a 1x. That means you're just checking one wire. It also has a 10 times. That means they've wrapped this wire around 10 times inside. so I can clamp my ammeter around it and get a more accurate reading. I just have to remember, though, as I'm checking it, I have to move that decimal over one spot. Divide it by 10. What's 4.5 divided by 10? All right, 4.45. I just moved the... Never mind. Use your calculator. Here, it's a 10 wrap. So now I'll pass it around. You can see where to put your leads to check voltage. You can see the 10 times wrap and the single times wrap. Interesting, huh? That's how that meter's reading those amps. It's pretty neat, huh? Yeah? No?
10 times, 1 time, okay.
10 times wrap. All right, let's go to DC for just a moment. We're going to come back to this. We're going to go to DC for just a little bit. Let's say we have the battery. And let's make this one a car battery. All right. What labels do you have in the car battery? Yes, we have the positive side, and we have the negative side. Negative side is usually what color? Black. Let me see if I can find a light marker. Okay. So which way does electrons flow?
To the positive side.
They flow to the positive? You saying they flowed from negative to positive?
No.
Anybody? Who said they flowed from negative to positive? So everybody thinks they flow from positive to negative?
Yep.
Everybody agree? Nobody disagrees with that? Cool, you're all wrong. Electrons flow from negative to positive. What? What kind of charge does electrons have? Negative charge. So that means on this side, I'd have to have more electrons, right? And on this side, since the proton is in the nucleus, that means that there's less electrons over here. So if there's less electrons here and more electrons there, because it's negative charge, which way is it going to flow? It has to flow from negative to positive on batteries. What? So your car battery, your whole frame is full of negative electrons, and they're all trying to get back to that positive side. So when they say on your battery, remove the negative terminal first, so that way you're stopping from flowing out of the battery. Yes, sir. On a car, we hook negative to the chassis, to the metal chassis, but it's still flowing from there, trying to get back to positive.
Yeah, so if you leave the negative on and you touch the chassis and touch something else, it'll still shock you.
Could, yeah. Or from another vehicle, another power source, or something else in there. Maybe there's a capacitor sitting around, especially speakers have capacitors now that hold the charge. But the way the electrons flow is flowing from the negative side to the positive side. And yeah, on the cars, we hook negative to the ground of the car, but it's not an earth ground.
So what's the dead battery?
What's that?
What's the dead battery?
Dead battery. Oh, that's a good one. I like that. Dead battery means we have the same number of electrons on each side, and there is no longer a potential for electrons to flow. So if, let's see, 1, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9, 10, 10, 11, 11, 12, 12, 13, 13. There's 13 electrons on this side, 13 electrons on this side. Is there going to be any push?
No. There's no.
Is there going to be any force? No flow. There's going to be nothing to make electrons want to flow, and it's a dead battery. There's going to be no flow of electrons, or at least not enough to start the car.
And then you're sad.
Then you're sad. Then you're going to have to hope you wish you had that AAA.
So when it won't hold the charge, then what does that mean?
That means the components inside the battery that allow the electrons to be on one side or the other is no longer doing what they're actively doing it. I went to the Titan Missile Museum there in Arizona, and they say their batteries, they keep the batteries dry. They flow the electrolytes or the electrons into the battery when they're ready to launch it, so that way the batteries don't go dead. I was like, what? I didn't know that was a thing.
Yeah, I didn't.
I guess when you're working on a multi-million-dollar, you don't want a $5 battery to kill your...
It's true.
Halfway up.
Yeah.
That's a
Pretty cool though, huh? Did you guys ever think that it flows from negative to positive?
No.
Yeah, well it does. On DC it does.
DC.
DC. But it's still flowing. It's just flowing from the negative side to the positive side. Interesting. Questions? It's a good question. It's just weird, right? Because we always thinking of it flowing from positive to negative, but nobody ever said otherwise. We just assumed, right? The positive terminal and the negative terminal, nobody ever said which way it actually flows.
Yeah.
But now you know the true way it's flowing is from the negative. The electrons are leaving this side and going to that side.
So technically you wouldn't start up if your battery for your negative was bad.
Yeah, well, if either one of these
Yeah.
was bad, it would.
I'm just curious. When you jump in a car, you want to check the negative off first before you take off the positive?
I've never taken the cable leads off when jumping a car.
No. Like,
When
when
you're
you
done.
connect the cables from your car to their car. which one
Oh.
do you take off for?
Don't matter.
I don't know. Here, officially, whatever your owner's manual says.
Yeah.
Safe.
Yeah.
But it don't matter, right?